Immunology Insights, Basics and Beyond. Chapter 22. The Memory Response. Marcello here. Welcome back to Immunology Insights, Basics and Beyond. In our last chapter, we explored clonal selection and expansion, the process by which antigen-specific lymphocytes proliferate and form an army of defenders against pathogens. But how does the immune system ensure that it responds even faster and stronger upon subsequent encounters with the same pathogen? That's where the memory response comes into play. Today, we will discuss how immunological memory is formed, the different types of memory cells, and why vaccines rely on this process to protect us from infections. So let's talk science. Let's start with what is immunological memory? Well, immunological memory is the ability of the immune system to recognize and mount a faster and more efficient response to previously encountered pathogens. This key feature of adaptive immunity ensures long-term protection and is the foundation of vaccine-induced immunity. After an infection or vaccination, a subset of activated B and T cells do not undergo apoptosis or cell death, but instead differentiate into memory cells that persist long-term, ranging from several months to many years in the body. When these cells encounter the same pathogen again, they respond much more rapidly and effectively compared to a naive immune cell. There are different types of memory cells. We have first the memory B cells. These cells remain in circulation after an initial infection and quickly differentiate into antibody-producing plasma cells upon re-exposure to the same antigen. Second, we have the memory T cells with different subtypes. For example, the memory CD4 positive helper T cells. They aid in coordinating the immune response by activating B cells and other immune cells. And the memory CD8 positive cytotoxic T cells. They quickly recognize and eliminate infected or cancerous cells upon re-exposure. There are additional subtypes of CD4 or CD8 positive memory T cells. For example, the central memory T cells or TCM. They reside in lymphatic tissues and retain high proliferative potential. Then we have the effector memory T cells or TEM. They are found in peripheral tissues and provide immediate immune responses. And last but not least, we have the tissue-resident memory T cells or TRM. They stay in non-lymphoid tissues, ensuring a fast, localized immune response. The different subtypes of memory T cells hereby guarantee that in each tissue and for each specific reaction, there is always a subset of memory T cells available. These T cell subtypes ensure a rapid immune response that is more efficient than in the primary response. Generally, memory B and T cells can persist for months or decades, with some memory B cells providing a lifelong immunity after infections like with measles or chickenpox. But how does the memory response work? First, we have the initial exposure. Upon first encountering a pathogen, naive B and T cells become activated and undergo clonal expansion. Second, we have the formation of the memory cells. Some of the activated lymphocytes differentiate into memory cells rather than effector cells. Third, we have the secondary exposure. If the same pathogen invades again, memory cells recognize it immediately and trigger a rapid and robust immune response. Fourth, we have faster and stronger responses. The memory responses lead to a faster activation of the immune cells, higher levels of antibody or cytotoxic responses, and a more effective immune defense with minimal symptoms. This is why after an infection was first encountered and probably caused some symptoms, reinfections actually remain asymptomatic. Next, let's have a look at the role of immunological memory in vaccines. Vaccines work by mimicking an infection, exposing the immune system to a harmless form of the pathogen or its components, thereby triggering the formation of memory cells without causing actually the disease. This allows the immune system to respond swiftly if it accounts as the real pathogen in the future. There are different types or approaches to vaccines. First, we have the classical live attenuated vaccines, for example used for protection against measles, mumps or rubella. They provide long-lasting immunity by stimulating strong memory responses. Second, we have inactivated vaccines, for example used for the prevention of polio or hepatitis A. They require booster doses to maintain memory cell activation. And third, we have the newest addition to the vaccine collection, the mRNA vaccines, for example used for COVID-19 protection. They instruct the cells via mRNA to produce pathogen-associated antigens that generate a robust memory response. Immunological memory plays a fundamental role in both health and disease. Of course, when it comes to protective immunity, immunological memory provides a long-term resistance against infections such as chickenpox, measles, and influenza. But they can also play harmful roles, like in autoimmune disorders. Conditions like rheumatoid arthritis or lupus have the memory cells mistakenly attack the body's own tissues. And then in chronic infections, some pathogens like HIV evade immunological memory, making it difficult for the immune system to clear the infection. To conclude, immunological memory is the reason why we rarely get sick from the same pathogen twice. This remarkable feature of the immune system allows us to mount rapid and efficient responses, providing long-term protection and forming the basis of vaccination strategies. In the next chapter, we will explore the contribution of Louis Pasteur, a pioneer in immunology who revolutionized our understanding of infectious diseases and vaccines. Before closing, I have a small request. If you enjoyed my content and want to hear more, like and subscribe. It's a small step for you, but it helps me a lot. So see you next time and thank you for listening.